There we go. Hello, friends. Thank you for braving the wind to come to our last week together. It's so sad. I don't know. Maybe you're not sad, but I'm sad. It's like teaching gives me a rhythm to my week that without it, it's like I just have too much time. I don't know what to do. So it finally happened. We went shopping at Kohl's this weekend, and my husband picked up a shirt, and the price on the tag was actually the price. I didn't even think that was possible. But he picked it up thinking, oh, I like this shirt. $50? I don't think so. Beep. Really? $50? So we did not get the $50 shirt. But we did earn $20 in Kohl's cash for shopping there. And so, yes, I have to go back this week to spend said Kohl's cash. And he's likely getting his $50 shirt with part of the proceeds. So that's good news. A couple logistical things here. Several of you have never used Mplus before, right? Yes. Okay. That's not a problem necessarily. I have examples in Mplus, and so I'm going to have to go over it because SAS is going to not be able to do everything we want to do this week. I will point you to, on the Piles of Variance website that's linked from the course page here, there is a general notes about program syntax and models. I have a section under Mplus here that if you're not familiar with Mplus, or even if you are, it might be useful to take a look at this. It just has sort of rules about syntax. It describes what kind of data structure you need, gives you example code for how to export data so that you can use it in Mplus. And pertinent to the models that we're going to be looking at, there's a whole section on this like between versus within modeling, the multi-level version of Mplus. It is non-trivial to understand, and I actually ran into some things I didn't even know in building these examples. So there's a section in here about what it means when you list variables on various statements and things like that. So that should give you a written version of the things that I will say that should be helpful. I also have heavily annotated syntax so that each of the code lines should be relatively self-explanatory. So I just wanted to point out that resource for you. We are not going to get to everything that I've either revived or built for this week, but part of my logic in building it is actually because I accepted a workshop at Oklahoma State University on modeling with in-person association, and I had wanted to build new materials for the multivariate section, so I said, well, can I go talk about that? And they said, sure. So whatever I don't get to, I will get to talk about in 2 weeks. I don't know if they're going to let me put it on YouTube or not, since they're actually charging people and stuff, and they're paying me and everything. But if they do, then you can check that out, and if not, then at least you'll have the materials. It will be largely overlapping with what we're doing this week, plus a few other things. This weekend, I'm headed to Illinois to do the introductory version of it, and you guys don't need to download any of this stuff because you have it already. It is remarkably similar to what we did last semester. So, all right, more logistical things. Homework. I don't know what's up with the website. Every time I post new data, I can get it back, but you guys can't. So I don't understand. It's something with smarterasp.com that I have yet to figure out, but I apologize again for screwing that up. But hopefully now people have green boxes, at least some people do, if you've tried. Any questions on homework that I can help you with at this moment? You still have like 2 weeks to do it, so yes, ma'am. Question 5. Okay, let me pull that up here. I will be person 1 today. ICC. Okay, question 5. Yes, the expected correlation between occasions from the same day and the same person in cortisol.
My answer is the sum of level 2 and level 3 divided by total.
That should be correct. Make sure you're keeping enough digits after the decimal. Okay, I may have to look at it. Same one? Okay. Then it's possible there's an error in my code somewhere, so I will have to track that down and see if that's working. Has anyone else gotten question 5 right? Who's tried? You've got it right? No. Okay, that 3 points makes a line. I think that's probably an error on my side, so I will have to check into that, and I will fix it somehow. I may need to fix either the question or otherwise just give you the answers, because I don't want to mess with the database when it's in action. So, okay, well then I will fix that later. Anything else I'm forgetting? No. All right, new stuff, brand new stuff. So yes, this was reviving a lecture that I was really not happy with for a long time, and now I get a chance to do it better, so I'm very excited about this. Multivariate, finally. So this is probably the most modern section. Stuff that can be done in software changes all the time. So in all my stuff, I reference like what version of Mplus I'm using, for instance, because what 8 can do is different than what 7 can do. So this is really the cutting edge, I would say, of the world of multilevel and the intersection of multilevel and structural equation modeling. So we're talking about then, how do we go from univariate models to multivariate? So you may have been thinking, we've been doing multivariate analysis this whole time, right? Yes, in the sense that if you have multiple observations from the same sampling unit in one variable, that's still considered multivariate. So occasions within persons, or if you think about people as multivariate observations in a group, it is multivariate data. Multivariate just means that the observations are correlated because they come from the same sampling. I'm talking about fitting more than one variable that is measured over time or over persons at the same time. So if you have two different measures of, let's say, depressive symptoms, and you're trying to look at an effective treatment, you may want to know, do each of them improve? Does one improve more than the other as a function of treatment? To be able to look at, say, longitudinal trajectories of depressive symptoms two different ways at the same time, you need a multivariate multi-level model. So multivariate means more than one variable at the same time. This entire time when we've been in proc mix, we've been predicting one thing. DV equals on the model line. So now we're transitioning from that framework into predicting more than one thing at the same time. You can trick SAS into doing it a little bit, but to do it more flexibly and to be able to test most of the types of hypotheses that you guys would be interested in, we have to move to Mplus or some kind of structural equation modeling software. So remember this, time-varying predictors. So I'm focusing the context of this back to just longitudinal, but everything that I have to say applies to cluster data as well. So time-varying predictors, level 1 predictors in more generally. Let's say that we have occasions within persons. In a univariate approach, which is what we've been doing, you have two choices for how you set up the model for a time-varying predictor. So we've talked about what happens when you do what we call person mean centering or variable-based centering more generally, right? So if you do it this way, at level 1, you have taken your original level 1 predictor and carved it up so that the level 1 predictor that goes in the model only has level 1 within variance to it. Consequently, it can only have a within level 1 effect. More common, though, is to not do some sort of variable-based centering and to center at some sort of constant, what is known as grand mean centering, or really just centering at any constant, including not centering at all if 0 already means something. If you put in this version of the predictor at level 1, it still has both its level 1 within variance and its level 2 between variance. So if you put it in all by itself, it's smushed because one effect cannot do the job of two predictors. So to solve that problem and to pair with the within-person variable, if you do it that way, we have the person mean variable at level 2. So we have person mean whatever or group mean whatever centered such that 0 means something, and it indicates the total between effect if it's paired with the variable-based centering within-person variable here. So if within-person x is purely level 1, then what person mean x has to do is purely level 2. If person mean x is paired with time-varying x instead, then what person mean x is the contextual effect. It's the difference of the within and between effects. It's the extra effect of the person mean after controlling for the absolute amount at level 1. So you will see in notes in my syntax this language of contextual between versus total between. They're both level 2 effects. but they mean different things. Contextual is after controlling for the level 1 predictor. Total between is not. So if you take your within plus the difference of between and within, which is the contextual, you get to the total between. So this slide is going to be really important for understanding what you get out of Mplus in particular. Because if you set up these models one way, you get contextual effects. If you set them up another way, even if it's exactly the same model, just a different version of the syntax, you get between effects. And I found out today that you can get some of both for no apparent reason. That was the thing I built this morning. So this is tricky. This is job security at the highest level, if you can negotiate this. All right, with me so far? This all sound familiar? So to depict this graphically then, this is what it looks like if you do a smushed effect at level 1. If you stick the original level 1 predictor in, centered at a constant, all by itself without anything at level 2, it's trying to do the work of both level 1 and level 2. Its level 1 and its level 1 variance are smushed together, and it has only one effect, which means that effect is smushed together. It's usually more heavily weighted towards the within effect because the level 1 sample size is bigger than the level 2 sample size. So the way that we fix it, if you want to keep your original variable at level 1 like this, is we add the person mean. So then the person mean picks up this level 2 contextual effect to get up to the total effect, which is the sum of the contextual here in teal and the within in purple. So it's the extra piece that level 1 doesn't already do. In person mean centering, it's much more direct. We take our original x and we carve it up into boxes. Boxes mean observed variables in most of these sorts of diagrams, whereas circles mean latent variables or things that are variance components estimated by the model, or what I would call piles of variance in this class. So we've taken x and we've built a level 2 box that carries only level 2 person between information, and we've built a level 1 box that carries only level 1 within information. Because that's the only kind of information each has, the only thing it can do is be that kind of effect within or between. But if you look at this picture, there's an asymmetry here that may bother you, and it bothers a lot of people. Why are we making boxes on the x side but circles on the y side? Because conceptually, level 2 person mean variance is the same thing as random intercept. We talk about random intercept as person mean differences. Well, person mean differences, right? It's the same. And likewise, if we take the deviation from the person mean, that's the same thing as a level 1 residual on the y side. The reason that we have this asymmetry is because in programs like SAS mixed, SPSS mixed, data mixed, LME4, I'm probably forgetting others, but all of these multi-level modeling programs, you can only have one Y. But in other programs, you can have more than one Y. So we're going to switch it. Ready? Watch. That's the switch. Univariate, multivariate. We're going to take x's at level 1 and functionally treat them as if they were y's. We're going to allow the model to carve up their variance in the same way that we allow the model to carve up the variance for y. Now, whether you think about x as another outcome or whether you think about it as a predictor is immaterial. The big difference is that x is now in the likelihood. That means it has distributional assumptions, it can have missing data, and the model will carve up the variance into each appropriate level. So person mean centering is the poor man's way of doing multivariate modeling. Brute force partitioning into observed variables to get really what we're after is right here. So this switch from boxes on the x side to circles on the x side, I call that multivariate multi-level modeling because that's what it is. It is probably more frequently known as multi-level structural equation modeling, MSEM. That drives me insane. My rationale for why I don't like that is, do you see a measurement model here? Nope. When you hear SEM, don't you think measurement models, right? Well, the reason that people call it that is because people call those piles of variance latent variables. Random effects are latent variables. So from that perspective, this is multi-level structural equation modeling. I don't get it. I call it multivariate modeling, multivariate multi-level. So you can call it whatever you'd like. If you're trying to be straightforward, call it multivariate multi-level. If you're on a job interview and you want to sound fancy, you're doing multi-level structural equation modeling, damn it. That's what you're doing. And don't forget it. So I have the word, in Chapter 9, I add the word truly here to differentiate ways, software approaches in which you trick univariate software into doing that for you versus you can do it directly. SAS, we will trick into fitting this type of model. There's only one catch, though. In SAS, these associations between variables at each level have to be covariances because they're going to show up in the G matrix and in the R matrix. We're going to fit random intercepts and slopes for multiple variables at the same time. All of their covariances are going to get estimated at the same time. So we can look at the extent to which level 2 is related on X and Y, and level 1 is related on X and Y. But we can only do it as a covariance, which means we can't actually fit the model in this picture where one is predicting the other. That also means we can't have things like moderation. I can't test as a covariance being different as a function of some other variable. And I can't test random effects of the level 1 association. So that's where the differentiation of a truly multivariate comes in. You can do all that stuff and more. So why not do everything this way? Well, because these are latent variables. So pros, it's flexible. It makes sense to treat X the same way you treat Y. There's also some simulation studies that suggest that the level 2 effect is better, or I'm going to say stronger. It's unclear whether it's better. It's stronger, but it's less precise because the model has to estimate the variance that you previously put in a box, and it has a hard time doing that, especially when intraclass correlations are small. So there's some evidence that suggests that treating it as a model, this version, is better than that version, which makes sense. So why not always do it that way? REML. Mplus doesn't have REML. No structural equation modeling program has REML. So if you have, say, let's see, Heather, you're doing fragile X data, you've got, what, 30 people, and you want to do this? You got to do it in maximum likelihood if you do it in Mplus. How does that suit you? It's like, no, that's not good. In small samples, variance components are going to be underestimated in maximum likelihood, which means standard errors are underestimated. And does Bayes fix it? Maybe. It turns out Bayes is not a good idea for small samples if you go with very diffuse priors. It works the same as REML if you go with priors where you know the right answer already. How often does that happen? Not so much. So the jury's still out on best for small samples, but that is a big caveat. The other piece is what happens when you put in interaction terms. So if I have, like in homework, what was the cluster data homework? 5, 6? Remember? Yeah, somewhere in there. I had you do this type of partitioning to 2 different variables and estimate 4 different interaction terms, right? The level 2 by the level 2, the level 2 by the level 1, the level 1 by the level 2, and the level 1 by the level 1. And the model was fine, right? You put those variables in, you put stars between them, it spit it out, it was fine. That would be impossible. Or it would take very, very long and maybe not ever work in this approach. Because when you fit interaction terms among latent variables, it requires numeric integration to do that, or Bayes. which is the same computationally intensive thing that we talked about for generalized models, where it has to try on a whole bunch of things. And you can maybe fit one interaction per model, maybe two. I reviewed a paper talking about fitting these interactions, and they did a simulation, and they had some example data as part of the paper. So I actually downloaded it, and I tried to fit 4, and it blew up. In simulated data, it blew up. So that was very discouraging. So yeah, it's not a panacea. When these models first became available, when I was teaching this class, maybe 2010 or something, I got really excited and I wanted to have all my students use them, and I had a project that they got to do, and every single person had to simplify what they were doing to make it go. Every single one. So if you get past maybe 2 or 3 variables at the same time, things start to go badly, because that's a lot of stuff to estimate, unless you've got a ginormous sample size with which to do it. So there's a reason why, even though this is theoretically more appealing, we may be stuck with this. But the good news is that all of the concepts that you've learned about how to do multi-level modeling, how to think about levels of analysis, how to think about what these effects mean at each level, how to test random effects, how to test fixed effects, what kind of fixed effects, what kind of random effects you can have, all of that transfers. We're still going to do likelihood ratio tests, test random effects. We're still going to think about levels of analysis and interpret things as within or between or contextual. It's just that we're going to do it for more than one outcome at a time. All right. So when do you not get a choice between boxes and circles? When your X has individual differences in change. So there's an extended treatment of this in Chapter 9. But I did a simulation in there basically to prove, and I will say prove because in the mathematical sense you can show it, that if you have a predictor that changes over time, if it only has a fixed effective time, you're fine with person mean centering, so long as you put a fixed effective time in the model for the outcome, because then the effect of the predictor is after controlling for time, which is exactly what we want. But if your predictor, your time-varying predictor itself, has individual differences in change, and you don't fit that, you do person mean centering and you build a level 1 and a level 2, you should actually have 2 kinds of level 2 and you only have 1. So what ends up happening is that the level 1 effect is biased by that slope variance that's still lurking in there that you didn't separate out. So in that case, if you have what you're thinking of as a time-varying predictor, but it also needs a growth curve to it, you got to do it this way. Have to. There really is no workaround. All of the workarounds that you can think of suck. I'm serious. Like they're bad. Don't do it. So this is the point at which you don't get a choice. You have to do a multivariate model if you're modeling 2 variables or more that each have individual differences in change. Yep. Well, so you think about this x variable as having 3 different kinds of variance in it, the same as y, and each of those kinds can have a unique effect. There can be intercept relations, slope relations, and residual relations. If you don't put this slope in the model, this effect that's missing actually shows up in here because the slope variance came out of the residual. So if you don't separate out the between-person slope variance from the residual, then you get a mixture of this slope effect and this residual effect as what you're calling level 1. So it's another kind of smushing, essentially. So, of curves. So yes, I am talking about the intersection of what you could call this a multivariate latent growth curve or a bivariate latent growth curve in the sect of 2. You can also fit this as a multi-level multivariate model. Multivariate multi-level. And I'm going to show you how to do all of it. So this is where the intersection of the classes I teach happens, and the classes that you may have taken, SEM and multi-level. Because random effects are latent variables, you can think about a lot of these questions and models either way. Question? Are you waving at me? No? Okay. It's like a little thing. You're waving at me. Yeah. Do you have a question, Lucas? No? Okay, all right. Now it's your turn then.
So I've seen people model latest different scores and then that way the bivariate change and like because I've seen, you know, like the bivariate.
Yeah, the stupid rows of circles with the no. I hate that model. I'm sorry. I can't even pretend. I haven't proven it yet, but my instinct is that because of the weird way they've defined the slope, the level 1 effects are actually smushed. The change score effects. I haven't proven it yet, but it's an instinct that I have, and that's one of the papers I'd like to write, is just making people stop it with that stupid model. Yeah, the different score models are so that you can ostensibly get change predicting level and level predicting change. But the thing is that you're commingling level 1 and level 2. Change is both constant person differences in slopes and within person deviations from that. And I think the way that they've set that up commingles the two in a way that is dissatisfying to me. That's one of the models that if you want to sound fancy, you can try that one. But if anyone asks you to interpret any parameter, good luck. And actually, in the papers that use that model, you will find them ignoring every single parameter except for those cross-lag things. But you can't interpret those in the absence of understanding what is going on in the slope. So yeah, don't get me started on those. But no, that's my thesis statement on there. All right. Other questions? All right. Well, then let's look at some stuff then. So yes. Trying to give you an overview then of how this is going to go. Multivariate, multiple level 1 outcomes. Multilevel, multiple dimensions of sampling. So we're putting the two together. There are 3 ways to estimate these models using maximum likelihood. Univariate MLM, that's what we've been doing. This is where you have to carve up your time-varying predictor into boxes. You cannot use this option if your time-varying predictor has individual change. It's good because it offers REML. It's easy. So even when I'm going to end up with a multivariate model, I often start in SAS looking at each outcome separately just to get a sense of what's there before I try to throw everything into the same model because it's easier to troubleshoot. And there's also, it's more convenient sometimes to work with this type of syntax where you can have more than one model in the same program. Truly multivariate MLM, which is in Mplus using their between and within. I don't know of another program that does that the way that they do it. So it's not to say that Mplus is the only way, but that in my experience I haven't seen anything else. But you can fit many of the same models as single-level structural equation models. So this truly multivariate approach is what they call MSEM, multi-level structural equation modeling. Regular flavor structural equation modeling in any of those programs can do these models as well, provided that you have balanced data or you're using T-scores and Mplus. So we'll look at examples then that do the same model all of these different ways. I will say that within structural equation modeling in particular, there's a lot of bad examples of time-varying predictors and smushed effects in that. So I will teach you how to not be one of those people as well. So why would you do this? 2 main reasons to do a multivariate model. Looking at relations across outcomes. So you can think of this, examples of this would be just like what I said. If you want to know if someone's slope correlates with their slope on another variable, like if I change a lot on this variable, do I change a lot on that one? If you want to phrase that as mediation, you can do that. So any kind of associations, regressions among the different variance components would be a reason to do these models. The other one is to examine differences in the effects of predictors. So that was the example that I started with. If I have 2 measures of depressive symptoms and I want to know if my treatment has a bigger effect on one than the other, I have to put them both in the same model to answer that question. So Katie, who just got a brand new fellowship and is on Cloud 9 today, she's going to do this in her dissertation. She's getting a fist bump from the room. So you have, let's see, you're going to scare small children, and the IRB's fine with this, right? Yep, okay. So you're going to scare small children with scary movies, and they're going to watch a scary movie either with you, their friend, or their sibling, right? Okay, no friends anymore. Okay, it's an evolving design. So you can think of those as multivariate outcomes. And you can look at differences between them, but you can also look at things like if their heart rate accelerates in this condition more than other people's, does their heart rate accelerate in that condition more than other people's? And so you are solidly on this slide, both in looking at associations between them, but also then differences in the effects of predictors, such as whatever demographic variables, if they have a bigger effect on their heart rate when they're with you versus with their sibling, et cetera, et cetera. So this is a fairly common type of question, so I want to show you how to do it. This can be done in any software. It's easiest to do in mixed, and so that's the first example we're going to do. And also difference score models. So if you have the difference between outcomes as something that's of interest. So I have an old example that I did not bring back. It's in this version of the class at Nebraska, though, looking at rats who got addicted to drugs on purpose. They made them. And so they have the difference in their behavior when they get saline versus nicotine. And they call that like adaptation, basically. They're looking at the difference of their response as the unit of analysis. And so they were taking different scores and sticking them in ANOVAs, and I was like, no. So if you're interested in the difference between outcomes as the thing you care about, you can fit them both in a multivariate model. Then you can predict each outcome and the difference simultaneously. And that's a more holistic approach than just modeling difference scores, which also tend to have funky variance-covariance matrices, and that's a whole separate question. So that's what we're going to do here. So questions so far? All right, and we have a few more slides to go, and then we'll look at an example. So multivariate associations of change. We can have questions about fixed effects or questions about random effects. So fixed effect, for instance, does my measure of depressive symptoms A decline more than my measure of depressive symptoms B? That's one question you might have. Is there a difference in the fixed slope across outcomes? But it's a different question to look at associations of random effects. If I have a stronger slope than other people on one measure, do I have a stronger slope than other people on the other? If my intercept is higher on this measure than other people, is it higher on this other measure than higher people? So those are between-person associations among the random effects. So here's a couple examples. This is from the octo-twin old people study that you've seen a couple times. I have a measure of functional change in grip strength on the left and a measure of cognitive change on the right. This is block design, a measure of abstract reasoning. These are what's known as spaghetti plots because it looks like you took a handful of spaghetti and threw it at the wall, and that's what you get. These are not spaghetti plots on your job interview. They are individual growth trajectories. The heavy black line came from a saturated means model. So if you want to know if cognition declines more than function, they'd have to be on the same scale for that to make sense, but you can answer that question by testing the difference in the slopes of those black lines. But if you want to know at the individual level, is this person who started out super strong the same person who started out super smart? And did this person who fell off the cliff here, did they fall off the cliff in cognition too? So these are associations in change as described by relationships among intercepts and relationships among slopes. Here's another example. Another example I did not bring back that's in the UNL version of this class, multivariate family data. So this came from my time at Penn State. They had a study looking at risky behavior in younger and older siblings from the same family. So the example from Chapter 9, actually, I made up some data that would be consistent with this type of story. And so we have the trajectories here for the older siblings and then for the younger siblings measured at the same ages. Well, we may want to know if there are cohort differences, if the younger kids differ on average than the older kids. But what we really want to know is this kid right here that went crazy at age 17, is that their little brother? Are there associations between family members in change? And to what extent would things like genetics or environment explain those associations? So that's another one. Here's another example that I decided not to bring back. It's in the UNL version, looking at ratings of positive affect and negative affect. So this is a fluctuation example. Clearly there's no change across days. This is just people bouncing up and down. But you could say, is somebody who tends to be up here in negative affect, are they the same person who tends to be down here in positive affect? And on days where you are higher than predicted on one, are you lower than predicted on the other? So associations between persons are stable things, intercepts and slopes that describe between person differences, but you can also have within persons. So this is what it will look like. So in these slides I have DVA and DVB. They can be whatever you want here. We're going to fit a G matrix that's going to look like this. We're going to have intercepts and slopes for both variables simultaneously. Multiple things on the random line. And if we have type equals unstructured, which we always do, then you get covariances here between the two intercepts, between the two slopes, and every combination thereof. So if all you want to do is look at associations between variables, intercepts, and slopes as covariances, you can do this in SAS. It's totally fine. You can do this in any of the other packages too, but it's easiest because you can trick univariate software into behaving like multivariate software if you want covariances. A couple caveats though, more random effects being estimated at the same time makes it more likely the model's going to blow up. So you will see in examples of this, they tend to have only linear slopes for that reason. It's not to say that you can't do it with more than one slope. The examples that I have are two piecewise slopes, but that it may be trickier. You can also get things where you have very large covariances that if you translate to a correlation look like they're big numbers, but they're still non-significant. If the variance itself is small, a really strong relationship may not be significant, so they can behave kind of screwy for that reason. We can also have level 1 associations. So this is the idea of variables traveling together over time after controlling for growth. So if I have my black DV and my blue DV here, they're very, very noisy, but on the whole, they're both going up. But if we look at how they go together in the residuals, on occasions where you are higher than predicted by your own growth trajectory, on one variable, are you also higher than predicted on the other? So this is what this type of picture illustrates. There is an association beyond just the fact that both of these are going up. They are tied together. This type of question, though, only makes sense for designs in which the measures are really collected at the same time. So Katie, in yours, you're going to have them watch a movie and then watch another movie. You're not going to do this because your residuals didn't happen at the same time. So you can just ignore this slide. Yeah, drop it, forget it. So the R matrix then is going to look a little different than usual. We're going to define the R matrix as the unique combination of person and categorical time. So something like wave or occasion, not the centered version that goes in model and random, but the one that goes on class. So we are assuming then that we have a type equals VC within a DV, but we're then estimating separate residual variances for each DV as well as their covariance. So this is type equals UN. If you want this covariance, you'll have to do something else if you don't, which I have somewhere in one of these slides, I think. There really aren't good extensions of alternative covariance structure models for this. There's a couple in SAS. You can have completely unstructured or various combinations of AR1. Those ones, that's the one place where there really isn't many choices for this in the multivariate framework. So, all right. How are we doing so far? Questions? All right, a little bit to go. So how do we test differences in effect size, and why would you? So let's say that we have the arbitrary line in the sand that divides effect size here, where 0 is meaningless, and any effect size that's past this arbitrary line is important and paper-worthy. Let's say that I have a fixed effect for DVA that is significant, and a fixed effect for DVB that is significant. Does that mean that those effects are the same? because they're both significant. Not necessarily. You have to be able to ask for the contrast between those two fixed effects. Is one bigger than the other, regardless of significance? Testing that requires both DVs to be fitted in the same model, both fixed effects in the same model, and ask for the difference between them. Likewise, this situation comes up a lot, actually. People ask me questions about this. I have a significant effect for one outcome, but not for the other. Are they different? Not necessarily. So this picture is meant to illustrate how this can happen. That arbitrary significance cutoff really doesn't mean anything in terms of effect size. So you would still need to be able to test the difference in effect size. It's possible that these are really the same. It takes more power to detect a difference in effect size than it takes to detect the effect in the first place. So how do we do this then? Here's just a slide about why you would want to do this anyway. Going to say that. Here's how we're going to trick SAS into doing these models. Katie, this one's for you. You're welcome. I had this slide before. I didn't just make it just for you, but I'm saying this is what you need to do. Okay. So we're going to take our longitudinal data, in which one row was per occasion per person, and we're going to stack it again. We're going to make it so that one row is an outcome for each occasion for each person. The code to do this is actually really simple, and I have several examples of it. So this is the data for one person for two measures, A and B, across 6 waves. This is what it's going to look like. So what we used to have as variable A and variable B in separate columns, that outcome is going to be one column. SAS doesn't know that we shoved 2 variables into the same column. It thinks it's still a univariate analysis. But through carefully differentiating the effects in the model with the code, we can get a multivariate model out of it. And this is something that when I read about it in Snyder's and Bosker and some of the older multi-level books, I had no idea what the hell they were talking about in that chapter. And multivariate models could not understand a word. Someone showed me the SAS code when I was a postdoc, and I went, seriously, that's all it is? So I want you to have that same sort of reaction, because you can do a lot of really cool stuff with this. So we've created here, then, 3 new ID variables. We won't necessarily need all of them, but it's a good practice to have them because odds are good that you might. DV, which is categorical. That's going on the class statement. It's going to be used to structure the R matrix. Then I have 2 dummy codes, DVA and DVB, where each is 1 when we're talking about that outcome. These act as switches. So if you need an effect for one DV but not the other, we will say DVA times that predictor, and then that predictor only operates in the DVA rows, because DVA is 0 if we're not talking about DVB. And likewise for B. So these 2 dummy codes are going to show up as interactions, but they function as switches. It makes it so that you can control which fixed effects and which random effects predict which DVs. So here's a model for you. This is what a multivariate multi-level model would look like. So the multivariate part is actually crossed at each level. SAS thinks it's 3 levels because of the way we set it up, but it's still functionally just 2. So note at level 1 here, Y for each time, for each individual, for each DV. So D is the 3rd subscript that differentiates which one we're talking about. In the level 1 equation, all terms are going to be multiplied by these dummy codes, either A or B. So what ends up happening is that when SAS reads through the data, if we're talking about DVA, that gets a 1 here. All of these terms turn on. If we're talking about DVB, all of these terms turn off because DVA is 0 then, and vice versa. So then we have, in this example, a random linear growth model that has a level 2 predictor of the intercept and on the slope, and it's as if you're just doing 2 multi-level models at the same time. Everything is separate. The reason to do this is to get the associations between the U's across outcomes and between the E's across outcomes, or to be able to test, for instance, whether the effect of this predictor on the intercept is bigger for DVA than for DVB. So here's what it's going to look like. Proc mix looks the same. We're adding DV as my categorical indicator here. Now, functionally, this code illustrates what's happening. There is a big thing you cannot forget. No int. That thing right there. That shuts off the general intercept and makes it so that we build our own everything. Every term on the model line is attached to one of these DV dummy codes. So outcome, remember, is our combo column that has all the DVs for all the occasions stacked together into one column. So DVA and DVB all by themselves, those are your fixed intercepts. It's a column of ones, right? That's what an intercept is. So I've shut off the shared intercept, and I've turned on separate fixed intercepts for each DV. Likewise, DVA by time, that's the fixed effective time for DVA. DVB by time, that's the fixed effective time for DVB. That's it. So on and so on. So this version of it, I think, is how I used to do it all the time. It makes it very clear what is being predicted by what. Writing it out this way also makes it so that if you don't need a certain term, so for instance, if you don't want this interaction term for DVB, you take it out, and it's only there for A. It's fine. Likewise, on the random line, there is no intercept. There are only the random intercepts of DVA and DVB. So each gets its own. Likewise, DVA by time, DVB by time gets its own. So let me test some intuitions about what happens here. What happens if I take this off? Yeah, DVB has a fixed slope instead of a random slope. What happens if I do this? They share it. If you forget the DVA and DVB interaction terms that create these nested effects, these switches, and you just write like time all by itself, you are making the random slope be shared across DVs. You're assuming that they correlate perfectly. That's an empirical question. Likewise, if I had something like this, let's see. Oh, come back. Time by pred. That interaction term then applies both A and B at the same time. If their effects are unequal, it's essentially like another kind of smushing. But if their effects are the same, then you can estimate one fixed effect to predict both things simultaneously and have fewer parameters. So there's a savings there if the DVs function similarly with respect to that fixed effect. Now that's a lot of typing. So if you understand how this works and you're feeling a little lazy, do it this way instead. I've replaced the switches with DV, which is on the class statement. When variables are on the class statement, SAS does the dummy coding for you. And the last one is the reference when you have an intercept in the model. When you take out the fixed intercept, it just makes two effects instead. So it does the exact same thing as the longer code up above here. this main effective dV is going to spit out one intercept for each level of dV. This dV by time is going to spit out one fixed slope for each level of dV. So whereas this code would be up here, the longer code would be twice as long if I were predicting 4 variables at the same time, this code stays the same because it understands that dV is 4 things if you put it on the class statement. Katie?
That's as long as you set the data up.
Yep. Yep. Same thing on the random line, by the way. It will create 2 separate intercepts and 2 separate slopes. This is the one I was thinking of. Then repeated. There's one thing to not screw up. Subject. It used to just be person when we had repeated. Now it's person by wave. Because we are defining the lowest level here as the unique combination of occasion and person. So what is repeated is dV at each occasion. So we have dV as the thing that's repeated. Type equals UN if what you want is a covariance between the dVs and each dV to have its own residual variance. Katie, you don't want that. You want the bottom one. Because your residuals aren't happening at the same time, so it doesn't make sense to covary them. So this seems somewhat convoluted, but this is heterogeneous topolets with a 1. That's a fancy way of saying, shut off the covariance, please, because it's predicting the first diagonal to be heterogeneous and nothing else. So there's no lagged covariances. There's no actual topolitzing going on. It's just UN without that covariance. So this approach then, for doing multivariate models in SAS, works if you don't want to know anything other than covariances across the outcomes, and what you're primarily interested in is the difference between the outcomes and their fixed effects. This syntax I like because it gives you the significance test for every single effect for every single dV as part of the model. You also get multivariate walled test for the combined effect. So like you'll get, for instance, you'll get an F test for whether there's a combined effect of time across dVA and dVB if it understands that those two are linked together by using this dV version here. And you can ask for differences as estimate statements. So as an example here, this is an easy way to make sure that you know what is being predicted by what dV. But if you want all the differences and you don't want to type them, then you can switch it. So here's another way of estimating this model that gives you a different version of the fixed effects. The big difference here, int is back. And we should have solution in here too, actually. Solution. And it needs to be blue. 1 second. There. So int is back. Now what the dV things do is create actual interaction terms. So the main effective dV gives you the intercept difference between each dV and the reference dV, whichever is last alphabetically or numerically. The main effective time is for the reference dV. dV by time tests whether the effective time is different for each dV, and so on. So if what you want are differences between the dVs, you can set it up this way and get that. It's whichever is going to be less painful to write out. I would still leave the random statement alone unless what you want is a difference between dVs, in which case you would set it up this way in the random effects. So that's it. Do you want to see an example? Why not, right? You know that's a rhetorical question. Okay, 9A. So these are the same data from Chapter 6 that we played with last semester. We're looking at change over time in two different measures of processing speed, a simple version and a complex version. The simple version, you had to see whether 3 numbers are the same as quickly as possible on 2 different rows, and the complex version makes you do it for 5 numbers. So these are called number match 3 and number match 5. I ended up taking response time in milliseconds and dividing by 10 because Mplus ran into problems with the size of the numbers otherwise. So these are in, I guess, deciseconds or something. So we're going to look at how these 2 variables change across 6 sessions of practice using a piecewise model, as well as to what extent age, as collected at the first occasion, predicts changes in each of these differently. So here's the setup then. So I have my 2 outcomes in my original data set. I'm building my piecewise slopes here. So I have slope 1, 2, which is the change between sessions 1 and 2. Slope 2, 6 is the change between sessions 2 and 6. They're both linear. Here's time-varying age that's centered at 80. Here's how you make a data set for Mplus. We'll come back to that when we get there. And here's what you do to trick SAS into fitting a multivariate model. That's it. I take my practice data set, in which we have 1 row per occasion per person, and I stack it again. Outcome. So here's my categorical DV. I created a string variable so that these labels show up on my output. I created a new common column called Y. You could call that's outcome in this case. And I created these dummy codes, although I don't think I end up using them. Output writes a new line of data. That's it. So here's your first multivariate model. It's an empty model. So here's what the equation looks like. The equation uses the DV3 and DV5. Here's the code. So I'm using my new stacked data set, added DV to the class statement. No int shuts off the general intercept. So now I have y equals DV. That's going to give me a fixed intercept per DV in this case. Random DV is going to give me a random intercept per DV. Subject equals person ensures that these are random person intercepts. Repeated DV then is for the combination of person and session. Session is my categorical version of time that shows up on the class statement here. And it's going to give me, using type equals UN, separate residual variances for each DV as well as their covariance. Type equals UN on the random line gives me all possible covariances on the random effects as well. Any questions so far? All right. I made new versions of the pseudo R-squared macro that will work with this. I think I put it up on the website, but if not, I will do that after class. So covariance parameters, 24. No, that must be from another piece of output. That one should be 6. 101 subjects, 12 observations per subject. So that comes from 6 occasions times 2 DVs. So here are my variance components. Here's my R matrix. So the first row column on this diagonal right here, that's going to be my residual variance for the first DV. That's number match 3, because it's sorted in order. This is for the second DV, so there's more residual variance in the more complex version. Their covariance is right here, but I also asked for R core, which converts that covariance into a correlation. So they're correlated 0.4. Likewise, here's my G matrix. This is the random intercept variance for the first DV. This is the random intercept variance for the second. So there's a lot more variance in the second task. It takes longer, so people are more spread out. And those random intercepts have a correlation, as given in G-core right here, of 0.9. So I computed the intra-class correlations for each of these over here. So DV3 has an intra-class correlation of 0.82. DV5 has an intra-class correlation of 0.76. So both of these have largely just person mean differences. These correlations then are new. We're not used to paying attention to correlations among the random effects. A correlation of 0.9 between the random intercepts. At this point, random intercepts are just person mean differences. That means if I am good at number match 3, I'm probably really good at number match 5 too. If I am better than other people, that's my random intercept variance, or worse than other people. Those two intercepts are correlated 0.9. The residual relationship then, on occasions where I am doing better than my own average, the correlation then in your performance is 0.4. So if I'm better than my own average in one test, I'm somewhat likely to be better than my own average in the other, but it's not a one-to-one correspondence. So far, there's no growth curves in these, though, so there's a whole lot lurking in the residuals that we don't normally hear about. And yes, Proc Lesa, trying to help your cause here with the labels on everything. And then the solution for fixed effects. The effect is dV, but then under the dV column, it labels what they are. How nice is that? So these are deciseconds. So it's 1,770 milliseconds is the average response time, and 3452 milliseconds for the other one. So the second one takes a lot longer, as you might imagine, to match 5 numbers instead of 3. All right. Questions? All right, so here I'm skipping a few steps. I guess not too many. I'm putting in my 2 piecewise slopes and random intercepts only in this model. So I have separate betas for each of the slopes for each of the DVs. They each get a fixed effect down here at level 2, and I still only have a random intercept. So here's my new code, dV by slope 1, 2, dV by slope 2, 6. That gives piecewise slopes to both. I am adding out PM to get a predicted outcome for each person for each DV so that I can do R-square later on. I'm also saving the fit statistics and the covariance parameters to do things with later on. So now after controlling for fixed time, the residual correlation is a little bit lower. And here's my results. So these are the slopes per DV. It looks like there is a larger amount of change in the second DV initially, but then not so much later on. So it looks like, just staring at this output, that the first DV, slope number match 3, continues to improve between sessions 2 and 6, whereas the second one does not. Now, does that mean that those 2 slopes are different? I don't know. They look different. They're both measured in response time, so they're on the same scale. But I have to ask SAS to find out that question, so we'll do that in just a moment. Here's my pseudo R-square for adding the fixed slopes. So is time a time thing or a person thing? Time thing, yeah. So that's why I bolded level 1 residual variance, because that's what's being accounted for here. So the fixed effects of change accounted for 24% of the level 1 residual in DV3, but only 7% of the residual in DV5. And yes, there's a results section at the end of this, so you've got all of my words here. Let's add some random effects. So this is an instance in which I am skipping steps. I'm adding both random slopes for both DVs in one shot. If I were doing this for real, I'd probably want to go one at a time, because a 4 random effect addition is quite a bit. But since you already know how to do that, I'm skipping the steps for now, and I know what's going to happen anyway since I played with these data. So I'm adding dv by slope to the random line for each of the slopes. I'm also adding code that's going to tell me whether or not my slopes are different. So I have the difference in the intercept here as just the main effect of dv. Minus 1, 1 compares the two levels of dv to each other. The interaction of dv by slope 1, 2 then, minus 1, 1 asks if slope 1, 2 differs across dv's as a fixed effect. Likewise, here's the test I'm probably more interested in right now based on what I've seen so far. Is the effect of slope 2, 6 different across dv's? And then here's an example of how you would do a combined test. If you want to say something like, is change different between two dv's? Change is both slopes. So here's a 2-degree of freedom multivariate wall test to do that. So Katie, this is what you need. So like for you, did heart rate accelerate more when you were with me than with your sibling? That's that. You're looking at a difference in slopes across dv, which for you is your condition.
How do you, what's the negative 1 and 1?
It's SAS language for a difference. If you have 3 conditions, then you would need to provide another number so that you have 3. So like if you had this combination, this would be the difference between dv1 and 2, leaving out the third. If you wanted to get then 1 and 3 instead, you would switch this to a 0 and this to a 1. So it just has to sum to 0, but you can think of it as this: what you want the difference between. One of them gets a minus, one of them gets a plus, and 0 means leave it out. If you wanted to do something like, is the combination of 2 and 3 different than 1, something like that, then you could do 0.5, 0.5, and minus 1. And that lumps together these two conditions and compares it to the first. So you can ask for whatever pattern you feel like. There. So here's my giant G matrix. And here's my giant G-core matrix. So these are the covariances and correlations, respectively, between all the random effects. So I've highlighted some in bold that are of note. Random intercepts, expected response time at the beginning of the study, correlated 0.8. So if you're better than other people on one test, odds are good you're better than other people on the other. Not too surprising. If we look at the covariances between aspects of change, 0.23, that's the correlation of slope 1, 2. So if you improve immediately more than other people on one test, you're not necessarily likely to do it on the other. Correlation of 0.2 is not all that strong. The last one, a correlation of 0.5, numerically is stronger. It's 0.65. So the extent to which you continue to change between 2 and 6 on one outcome is correlated 0.6 with the extent to which you continue to change on the other. However, if we go down to the covariance parameters table, I've labeled the ones that you would care about. That correlation of 0.6 is actually not significant. So this is what I was talking about. You can have what look like strong effects that aren't significant because the variances that they are referring to may not be that well estimated or may not be that large. And I have this right here next to it highlighted. SAS is giving me an error message referring to that as non-positive definite. The correlation between slope 1, 2, and slope 2, 6 for the second dV is 1. So it's at the boundary because it won't let it go beyond that. So that's potentially indicative of having too many random effects. But I wanted to keep them in so that I had a nice little example. And there's my fixed slopes. So in terms of what you get out of the model, the solution for fixed effects tells you if each predictor is significant for each DV. The type 3 test of fixed effects gives you multivariate tests combined across DV for each predictor. So like right here, like is there change from 1 to 2 across DVs? That's what that p-value means. And then last but not least, the estimates we asked for the differences. So the intercepts are significantly different. The fixed slope 1-2s are not. So even though numerically it looks like there's a greater improvement on slope 1-2 for the second outcome than for the first, those numbers are not different. These numbers, though, are different. The continued slope of -0.3 that is significant for one DV is significantly different than the continued slope of 0-something that is not significant. There's the difference in those slopes, and there's the p-value for that difference. So this gives you the whole picture. Is it significant per DV, and does it differ significantly between DVs? There's my likelihood ratio test for my slopes. Ta-da-da-da-da. Ta-da! See, isn't this nice and easy? Relatively speaking, right? It's like not that much of a jump from what you're used to doing. So we'll next time then look at how age predicts these things, and we'll look at some more examples using Mplus. I don't know that I'm going to be able to get through all of the Mplus stuff, and so I'm going to have to pick and choose, but I wanted to point out to you that in the files that I uploaded a little bit ago for this example, I have the SAS files, but I also have these exact same models using the MLM within side of Mplus as well as the SEM side. So if you want to know what this would look like as a structural equation model or as a multi-level structural equation model, there you go. So, all right, office hours start now. I will see you on Wednesday.